going to start about in few minutes. Okay. Uh, just wait some time for others to join. Okay. So this is session fifth session. Okay. We're going to cover the week 4 questions. These are previous year questions. Okay. So that you can do similarly with the questions that has been given this time. Okay. So this week comprises of optimization techniques, non-linear optimization techniques for optimization of neural network weights. Okay. So what we have seen is gradient descent, but we'll see the limitations of it and how to progress to other methods which perform better in usual conditions. Okay. Just wait for a few more minutes and then we'll start. Okay. So the topics that are covered here are just let me write those down. So first we see the how the lectures are synchronized is that Professor shows a um, that curve to understand the gradients. Okay. So we come up with one first approach is a momentum based approach. Okay. And so what we do is we take the update t minus 1, so it was previous update. Okay. And we have a some weight usually taken as like a high value close to 1. Okay. Plus gradient of the weight at time t. Okay. And this is update t. Okay. Now the w is updated this way. Okay. So this is the exponential moving average. We are averaging, that is correct, but you have to understand that this is not a simple average. Okay, there is a weight attached to it. Okay, in which the prior updates are given more precedence. Okay. uh, okay, then we'll get on with the questions. Just a minute. Maybe I should download the lecture notes as well. It would help us to see the things at hand. Okay, we'll start now. So, first, let us see the questions only. Okay, is this downloaded now? Hmm. It's done. So, first, we'll start off with the questions only. Mm, which is here. Hmm. Now, can you see the question here? Is it too small? I think it would be too small. This should be better, huh? So you're training a neural network. So you're given a neural network on a data set with 5 million samples. The total data set size is 5 million. Okay, using many batch gradient descent. So we're having a batch size like 32 or 16. These are the usual number which is taken. Let's see what is the number here. The mini batch size is 500, so they give it as 500. So you're making simultaneous gradient update taking 500 samples at a time. Okay, this is what it means. Each parameter updates take 100 million seconds, 100 milliseconds, sorry. So each parameter update takes 100 milliseconds. Okay, how many seconds will come? 5 epochs of the. Okay, so what is given is that one parameter update. So what it means is that you're having the gradient of the loss is taken. Okay, okay, with respect to the parameter wt. Okay, so this update, okay, this update takes 100 milliseconds. That is what is called of. Okay, so this is what we have. Okay, now so there are 5 million samples, and the batch size is 500. Okay, so 5 million, what does 5 million means is 5 into 10 to the power 6, right? This is 5. Batch size is 500. So how many gradient updates is actually required? Okay, so what you have to understand, for each batch gradient update is only once. Okay, so you understand, means like every gradient of each samples inside the batch is first accumulated, then the update is made. Okay, and so this is it. Okay, and so number of gradient updates that we have to calculate is this. Okay, this is 10 to the power 4. There are 10 to the power 4 gradient updates, and each update takes 100 millisecond. Okay, a millisecond is how much? 10 to the power minus 3 second. This is the seconds that will require, so 1000 seconds will be required. Acha, 5 epoch, but we have to do 5 epoch as well. Okay, so this is 5000 seconds. Okay, answer is 5000. Any doubt here? No doubts, right? Okay, see, we'll see the notes as well here, just to get the things crystal clear. This is the back propagation part. So all repeating. uh, Let it go. Okay, let's focus on the questions only. The slides are too big actually. You're comparing training times using different gradient descent algorithm on dataset with 1 million data points. Each parameter takes 2 millisecond. Each parameter update. Okay, so the data size is given as 1 million 10 to the power 6. Okay, and each parameter update takes 2 millisecond. This much. Okay, how many milliseconds longer will stochastic gradient descent take compared to vanilla batch gradient descent to complete 2 epochs? Okay, so the one is stochastic gradient descent when you're updating the gradient descent for each sample. Okay, so the number of samples 10 to the power 6. Okay, and for each sample there is a gradient update, and for each update takes this time. Okay, so to get the time, this is the time it is going to take. Okay, for one epoch. For 2 epoch, multiplied by 2. This is for SGD. Okay, okay. Now batch gradient descent. Now batch will have only one update. Okay, and okay, each epoch it will have only one gradient update. Clear, right? So how much time it is going to take is the question. Okay, so let's understand that. The data points are given. Each parameter update takes 2 millisecond. Now 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 you have to understand that. Okay, so let's calculate this one first. So this will become 10 to the power 3. Okay, so 4 into 10 to the power 3. So 4000 seconds. Okay. Now next what we have here is, now, so if you have to understand that for batch gradient descent, one in one epoch only one gradient update takes place, right? So what it will take is this time 4 into 10 to the power minus 3 second. Okay, how much more it is asking? So it is going to be almost 4000 type. Okay, little bit. Actually, it is in millisecond. Okay, so do in millisecond. So 4000 and milli, then this one. And this is 4 millisecond. Okay, you have to subtract 4 from this. Okay, so it is going to be, this is the answer. Okay, okay. So one thing you have to understand is why this question, you might think that batch gradient descent is very fast, but it is not correct that way. Okay, so what happens is that the gradient update, we take only one gradient update in batch gradient descent. Okay, but the another problem that we face here is that you have to accumulate all the gradients. Okay, let me show the slides, but slides are really big and I'm unable to find actually. These are all the back propagation questions are there. Okay, we get to our lecture. So in this, as you can see, so he was showing the this surfaces. Okay, and so you know this one, I think top here. So momentum based gradient descent we are looking at. Okay, and this is our update rule. Okay, so let me take a screenshot of this. Oh my god. Okay, whatever. So let me write it down. So this is a question we have, but so the thing we have here is that in momentum based updates, what we're having is that update, which I've already written this one. So okay, so this is the update rule, momentum based gradient descent. Okay, another what we have is the Nestor of momentum. Okay, but the slides are maybe it will not be required. Okay, we'll cover slowly. Okay, so let's go back to the questions now. Okay, now choosing the right batch size in resource constraint system is very crucial step. So what happens in how we choose the batch size is that when we are calculating the gradient updates, what we need is to select the batch size such that our computing device memory or RAM is fully loaded. Okay, as much as make the batch size as much as possible to make that happen. Okay, any more than that and the memory will overflow. Okay, and if you take the batch size too less, then the our computation device is not fully used. Okay, so this is one of the thing to consider. Okay, you're developing a real-time image recognition system for a mobile health application that must detect skin anomalies from photographs. The device has limited memory and battery, so optimization has to be efficient. Initially, stochastic gradient descent was used, but the result was unstable and slow. So what happens with stochastic gradient descent? There is the path of the gradient on the error curve is stochastic or like uncertain, and you can make mistakes while, and also it is slow. You're considering many batch gradient descent and analyzing the impact of the different batch size and optimization, both convergence and generalization performance. What is the most practical benefit of using smaller batch size on constrained devices? So smaller batch size is the thing that the memory of the device means because the smaller device memory will not be too much, so smaller batch size has to be taken. Okay, so minimizes memory usage and reduces overhead. You can understand why? Because the smaller device has smaller memory, the batch size needs to be smaller as well. Okay, you reduce the batch size from 4000 to 1000. What happens to number of weight updates per epoch? So how many weight updates are actually required? So you have to understand, if the batch size was, suppose the data size was 4000 only. Okay, then the batch then the weight update per epoch is 1, right? Easy. Now if the batch size is 1000, for each batch you need a memory weight update. Okay, and data set size is 4000, so 4000 with 1000 is 4, so number of updates required is 4. Okay, so the number of weight updates quadruples. Okay, which is the following statement true about the mini batch gradient descent? So mini batch gradient descent, we understand, means the batch gradient descent is takes the whole data set for gradient update, and here in mini batch uh, it takes some smaller values to make the updates. Okay, so compromise between computation and accuracy. Okay, prevents gradient vanishing completely, allows parallelism in training. It can be still prone to. So batch gradient descent is the most accurate one, and but mini batch is the more computational efficient one. Okay, because accumulating the batches then making one update is not feasible in most situation. Okay, so answer will be 5-1. Okay. Oh, there are many answers here actually. So parallelism in training, what does that mean? You can give some batches, okay, some mini batches to one computing device, another mini batches to another computing device, some other mini batches to another computing device, and then accumulate the gradient updates of all those devices into single value, and then do backpropagation. Okay, it can still be prone to overfitting. Overfitting problem is not dependent on batch size. Okay, overfitting depends on the model capacity, dataset size, and those things. Okay, just to give you an example, I present you my screen from this my laptop here, okay. Can you see my screen? So can you see this code that is running, the logs, as you can see? So you can see, right? So this is like a model I'm training, okay. So it has this many parameters, okay, like in millions actually. Hmm. So quite a huge model, okay. And these are the epochs of training, okay, time taken at each epoch. And this is the how much gradient, a norm of that gradient is calculated, okay, to see if there is no gradient explosion or something, or something like that. This has been quite useful, okay. And you can see the main thing is the learning rate here. So learning rate, you can see, steadily reduces, okay. So this is like a learning rate schedule that we called, okay. And this is the cosine annealing schedule, okay. So the learning rate progressively reduces, okay, and then once upon a time again increases. So what so so the theory behind this is that I will show it in the presentation itself, but so this is the scheduling of learning rate, which is quite important. Training loss is somewhat decreasing, not always. There is some increase and decrease, as you can see. This is a metric for convergence I've used, okay. So it is called IOU. It's a computer vision problem actually. So IOU is used in that. So this is what we have, okay. And so moving back to our presentation. Hmm. Where is my Meet app? Okay. Hmm. So I can present from the my tablet. Okay, now you're able to see. Okay. So what was I showing there? So it's called the learning rate schedule. So what you have, these are the error curves, let's say, and now then it becomes really close, okay, like that, okay. You can see, right, what I'm drawing. So as the gradient increases, as you can see, the gradient of the surface increases as we go inside, okay. So what should happen is that the learning rate should be high when the gradient is low, okay, so they can traverse quickly, okay, and then it should become faster, okay. So no, then what happens, the overshooting happens, okay, you can remember. So then the learning rate should be lower. So that is why I was progressively reducing the learning rate as the model training went further, okay. So this is called learning rate scheduling, okay. And so annealing is one concept, okay. So you have seen in the lectures as well. We'll step reduce the learning rate, okay, as the training progress, okay. And so this is one of the strategies. There are many other strategies you have seen in the lectures, okay, for controlling the learning rate, okay. I will take few other questions here. just wait a minute. Presentation has somehow broken. Now what was I saying? First need to present here, no? Now what was I showing here? This presentation, right? And here what we're doing? Acha, we're about to do the questions, okay? So now I paste the question. So you're training a neural network on a noisy data set of grayscale images, okay? So grayscale images means that there are no RGB, only one scale, okay? After 5 epoch, the loss is reducing very slowly. So loss is reducing very slowly. What can you do? Accuracy plateaus, not able to do much, okay? Gradient magnitudes are very small, okay? If the gradient magnitudes are very small, what does it means? That there is a flat surface, okay? Understood? You understand? Means the gradient magnitudes, if they're very small, then the very small gradients is the answer, okay? Because main thing is this gradient magnitudes are very small, okay? If the gradient magnitudes were like large, then it could have been like a large learning rate can be a problem, okay? That was why it was not updating. Maybe momentum, okay? Okay, due to momentum, incorrect noise level, this is unlikely anyway. But this you can understand because the gradient magnitudes are very small, so it denotes a flat surface, okay? So very small gradients, okay? Optimization would help improve learning in this situation. What optimizer? Okay, can a vanilla gradient descent can work here? So it will not work, okay? Mini batch also doesn't help. Momentum based gradient descent, what happens? You're having a momentum term, okay? So even with momentum it will still be slow because also in momentum you're taking the previous gradients into account, okay? It will be helpful in a way but not that much, okay? What happens with Adam is that, let me show you the Adam formulation. So in Adam what you're doing is that you are having two moving average expression here, okay? So one, you are accumulating moving average way the gradient updates, another is the second order, the square of the gradient updates, okay? Okay, so this is called like the, you can say this is like the mean and the variance, okay? So and what you do is you can calculate the unbiased estimator of it, okay? So it was shown here. Oh my god. So this calculation helps in unbiased estimation of this mean and variance term, okay? Understood? Then you make this update. What? So this update was actually we derived from. So let me show you the start of the thing, okay? So this was the thing. So so the three algorithms, ADA, GRAD, RMS, prop, and ADAM, these three algorithms denotes adaptive learning rate. What does it mean? It means that the learning rate is different for every feature that we are using. So these are the features, okay? For hidden layer, the features will be like the, as we have seen before, that for hidden layers, what you have. So these are the features, okay, the four features. So this will also have before the activation, the H1, H2, H3 that we have seen previous class. Okay, these are also features. So the learning rate will be adaptive with respect to these features, okay? Means different for different features. Okay, understood. So for that, what is done is, as means, so why it is required. So we see these two gradients with respect to weight w1 and w2. So this w1 weight is for the feature x1, this w2 weight is for feature x2. Okay, so if so that was given, if this x2 is very sparse, so what it means that it is most of the time zero. Okay, or very small, very insignificant. Okay, means in value, but can be a very important feature. Okay, suppose if it is large, just like once in a while, it like dominates the inference. Okay, you understood? Okay, so this is the situation. Okay, we have, and so this has to be given a higher learning rate, because what happens if this is small, the gradient updates are also small, that leads to less learning for this feature. Okay, so for that it has to be given a higher learning rate, as you can see. So this is the modified learning rate. So it depends on under root vt plus this epsilon is the numerical stability. For numerical small value. Okay, so it does not becomes a zero and division by zero problem doesn't happen. Okay, so the vt is denotes the vt. Actually, for with vt you can control the learning rate. So this vt is given by, so ADA grads simple averages the values. Okay, not exponential moving average, as you can see. Okay, so what happens is that uh, the features which are sparse are given more priority. Okay, and so so you can see this one. Okay, how is it giving that? So in case of, so whenever the gradient is large, suppose when suddenly this is large. Okay, that is actually averaged out, added to when it is small. Okay, so it does not fall fast. Okay, but what happens is that what ends up practically happening is that for features which are not sparse, it tends to like really damage them very quickly. Okay, okay, because in that case this will be large. Okay, so large dividing by large, learning rate will become very small for those. So the features which are not sparse are take a hit, then they are not able to learn properly. So for that they use a exponential moving average, so that the features which are not sparse are also still able to learn well. Okay, because their previous values are taken, okay, into account. So what does Adam does is that it takes a mean of the, so only difference you can see is this first unbiased estimation, and this mean term is also calculated. So this gradient, so 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 it takes this mean term as well. Okay, and this mean term is also taken into account. Okay, and as you can see this for weight updates, the previous updates are also taken into account. Okay, it's like the momentum term, honestly. Okay, because previous in RMS form or ATA grade there was no momentum term. Okay, and from derivation you can see this is actually an to make it an unbiased estimator. So it is not dependent on the beta 1 and beta 2. Okay, estimation is independent of them. It is quite important, you can understand. Beta 1 and beta 2 are our hyperparameter. Okay, and the calculation cannot be dependent on them. Okay, this is what we have. Now we will go back to the calculation here. So this is the bias correction, unbiased estimation. Okay, and adaptive learning rate. Okay, so this will help how, because so when the flat surface is there, the features are sparse. Okay, so this will help with this sparse feature problem. Okay, which of the following helps in handling small gradients? Okay, so let's take another screenshot here. So we need to handle small gradients here. So if the gradients are small, what does it mean? The updates are like very small updates. Okay. So how when the gradients are small, can be like a flat surface. Okay. So if flat surface is there, okay, you cannot reduce learning rate in that situation. What happens then? It becomes even slower. The gradients become even small using ADA grad. ADA grad you can use, but this is the better option. Okay, ADA. Okay, means right. Okay. Advantages of using momentum. So momentum has a faster convergence that's correct larger steps in the wrong direction. This is not advantage, of course. Okay, this is a problem actually. Helps escape shallow minima. Yeah, this is another advantage. What happens if you are at a momentum? So if there is like this is the curve we have. Suppose in gradient descent it will just stick out here. Okay, it cannot move out of it. Momentum it will escape and then go here. Okay, so this is another benefit of momentum. Avoid oscillation in steep slopes. Does it really help here? This is not the main benefit actually. It is not a benefit at all actually. Using momentum actually it leads to oscillation in steep slopes. Okay, this one is wrong actually. Do you understand? So what happens in momentum is that, so these are like the light slope, then steep, and then something like this. So it moves somewhat faster due to momentum. Then momentum become very large. Okay, then it overshoots. Okay, and then comes back like this. So it leads to oscillation actually. It does not reduce oscillation. Which the following would not help in this situation? Reducing learning rate. Okay, so this is simple answer. Okay, because it is already flat, then you're already again reducing learning rate, so that will not help the cause. Okay, so this is what we have here. In training a deep neural network, the optimization technique used is momentum based gradient descent. Okay, this is what we have. At each iteration, instead of only considering the current gradient, the optimization also includes a fraction of the previous update to help accelerate the learning and escape shallow minima. If the learning rate is 0.01 and momentum coefficient is this, the current gradient at step t is this. Okay, the previous update was 0.1. What is the value of the new update? Okay, let me show the equation here. This is the equation. Okay, so let me take a screenshot here and take this equation there. Copy. Okay, so let me write it down again. Maybe you can slow. Make it small. Okay, so like you can write it like this. Okay, this is what we have here. Okay, and let's see the question. Okay, now they say if the learning rate is eta, so the momentum coefficient is 0.09 and the this is 0.2. Eta is also there, I think. And the learning rate is 0.01. Okay, and previous update was 0.1 here. This is what we have. The value of the new update. So this is the what is they're asking, 0.09 plus 0.002, 0.092. Okay, done. Clear? Very nice strength, but nobody is responding. Are you able to understand? Any doubt, anything? Okay, we'll move ahead. Okay. Ready? Okay. So go back to our questions here. So a data scientist is analyzing how momentum affects learning speed over time. She when initializes a weight W0. So we have W0 weight here and uses the following parameters in momentum based gradient descent. Momentum coefficient is 0.8. Okay. So first, so update 1 will be alpha times update 0. So momentum coefficient 0. So update 0 will be 0 at first, right? And plus learning rate. Okay, learning rate, what is the learning rate? 0.05 into gradients. Okay, so it is minus 0.5. Okay, and W0 is equals to 1. Okay, now W1 will be equal to W0 minus UP1. Am I correct here? W0 is 1 and UP1 is, this is 0 and this is minus 0.025, I think. This is the one. 25 into 10 to the minus 3, 2.5 into the minus 2. Yes, this is the correct one. Okay, so plus 0.025 is W1. So this is 1.025. Done. Okay. But I think this is not needed. The W calculation is not needed. We only need the update calculation. That is what they've asked for. Okay. So next we go to the update 2 calculation, which will be 0.8 times update 1. Done. Plus, right? So this is minus 0.02. Okay. This is minus 0.01. This is minus 0.03. Done. Move on to the next question. Okay. So we've got minus 0.03. So again the update is minus 0.03 into 0.8 plus learning rate 0.05 into delta WT, which is given, right? Minus 0.3. Done. 8324. Okay, so that is 24 and 3 zeros. Okay, so minus 0.024. Okay, 5315 and 3 zeros, so 0.015. This will negative as well. Okay, how much is it now? This is 9 and this is 3 and this is 0. This is minus 0.039. Let's see if we got it right. We got it wrong. Maybe some calculation mistake. Let me check the calculation. This looks correct. Then this one. $200 and then 0.2, 0.02 minus 0.02. And this is this one. This looks correct. Then the calculation seems correct actually. So maybe your concept was wrong, something, I don't know. The first answer came correct. Okay, first question number 12. Okay, but this is not. Okay, what you have done different there? Here are we subtracting something here? No, no. So everything seems alright. I don't know what I've done wrong. Can you check? Someone check what has been done wrong. Any formula mistake, something mistake? I cannot come up with it actually. What I've done wrong. Anyone? The first question came correct. Okay. Next question. Doing it similarly, gamma equals to 0.8 momentum coefficient, which is the same there. Learning rate and update is 0, and then consecutive iteration, and seems correct actually. Anybody can point the mistake, or is the answer wrong? Anybody who can see the mistake? Something I've used wrong here. Seems to correct. I don't know. So the 3.9 I've got. It is 0.009. 3 is coming extra. If we actually here, if we add it, I think that we're going to get the answer. I think 14 minus 5 is 9. Okay, this becomes 0, 0, 0. Yes. This is the only term which is the different term actually. But the answer is they have given is minus 0.0 minus 0.3, right? So we're going to just use it, right? Any other problem? I think the answer is wrong here because as you can see, this is a straightforward thing. If this was plus 0.3, we'll get the answer. Okay, but I think I've done it correctly. Okay. Any issue? No issues. So let's see the next question. What are the benefit of using mini batch over full batch? So if you use mini batch, then less memory usage. That is correct. Okay. More frequent weight updates. Okay, that is also correct. Higher computational cost. That is not actually. Okay. Better generalization. Is regarding oscillation training a deep learning. You're training a 6-layer network on regression data, so the model experiences oscillation loss after 10 epochs. This is the thing we have. Okay. So we'll do these questions later. I want a break, okay, of 5 minutes, and then we'll come back, okay. Okay, so let us continue now. So these are the new questions we have that you have got to go through. So oscillations in neural network training. So it means that you're not able to converge to the minima, but you're oscillating between levels above the minima. Okay, so six-layer neural network. The model experiences oscillations in loss after epoch 10. So jumps around the minima without settling. What is the likely cause of oscillation? So oscillation never happens with too low a learning rate. You reduce the learning rate. If you do it perfectly, it will converge perfectly. Okay. So too high a learning rate can be a problem, because if it is higher learning rate, then so suppose it is here, okay, and then the gradient update is like this, right. Now the gradient is negative here, right, and this is the learning rate. So you're subtracting, so you're adding to the weights is here. Okay, this is error, this is weight. Okay, so it was previously here, let's say. Now it needs to go this side. Okay, and we're gradient is positive here, gradient is positive, so we're subtracting something. Suppose this becomes value becomes very large, then this will come here. Okay, then it jump. Okay, and then again the negatives, and adding something, if the addition is very large, then it go there. Okay, so they are the problem. So and depends on the learning rate, right? If the learning rate is too high, then it will jump. Okay, so higher learning rate is the problem. And batch size too small, batch size doesn't cause such problem usually. It can though, like batch size if small, then it will have more stochasticity, so it will have more jumping around. But the major problem is this: which technique helps reduce oscillation? So momentum does reduce oscillation, but it creates some as well, so it is not the best answer. But the optimization is to peak ahead before computing the gradient. So peak ahead is the master of accelerated gradient. So let me explain this one. But I have no something to show you. So let's use Google here. It's not very good actually. So let's see the classical momentum here first of all. So here what we are doing, you're first calculating the update and then updating the uh, parameter. Okay, but in Nesterov what happens is that there are various definition only, so it will difficult to explain like this. Okay, but so it helps to peek ahead first and then calculate the gradient descent. Okay, so the notes are very large as well. I have not written it down in Google. You find various definitions, so honestly hard to show. Sorry for that. And what happens if the momentum is set to 0? So if the momentum is not there, okay, Okay. See, the momentum parameter is set to 1, then it overshoots and diverges. The momentum is too much. You can understand. Means it not taking any new updates at all. Which of the following are the advantage of many batch gradient descent over? So reduces variance of updates. Main thing is this. Okay. But rest we have to see. Okay. Faster convergence. Okay. Now a few more questions here. Okay. So let's see to this. So recommendation engine that learns user preference in real time. So it recommends. It is classification problem. The model must adapt quickly, avoid local minimum, maintain stability during updates. You observe that these are the requirement. Adapt quickly. Okay. Avoid local minima and maintain stability. So for local minima, you need the momentum one. Okay. Adapt quickly. You can say the adaptive ones. Adapt maybe. Maintain stability during training. Okay, you observe the fixed learning rate phase to generalize well, so you need schedule as well. Explain to the line search. And so what is line search? It tries different learning rate while gradient calculation and choose the best one depending on the most reduction in loss. So what do you have with line search? Okay, so it reduces the it takes the best learning rate according to the most reduction in cost function. Okay, so this is the one. What is the key component of computational disadvantage applying line search in every update? More computation each step because it's trying every learning rate. Okay, with the following schedule require setting two hyperparameters. This exponential is one. Okay, because you need the k of the exponential as well. So it gives a decay of the learning rate, but decay parameter you don't need to set. Okay, 1 by t there is nothing. 1 by t also there is a parameter. I think t is the parameter here. Okay, constant learning rate don't need, and step also mean how many steps you want to reduce. Okay, so these are the answers. Exponential decay adjust learning rate using this which formula? So this is this one. Okay, next, learning rate is typically used to. Learning rate decay is typically used to fine tune the model towards the end of the training. So that is correct actually. Avoid oscillation near minimum. That is also correct. Eliminate the need for momentum. Momentum is still required. Okay. Control the impact of noisy gradients. Noisy gradients. So noisy gradients. Noisy gradient means that maybe the batch size is too small, so the gradients are not optimal. Okay, in that way noisy. In step decay, the learning rate changes at predefined intervals. So that's very easy. If you 1 lakh samples and batch size is this, so 10 steps are required. How many parameter updates did happen? 10. Okay. If n equals to the batch size is 5000, so this is 12, right? Number of weight updates per epoch is 12. Okay. You're training a neural network. Okay. Let's get to that. Two more questions are left. Okay. So large data set nested of accelerated gradient descent variant of the momentum based, unlike standard. Acha. I don't remember the formula actually. The problem is that. So let me see for the formula in the slides. Okay. So these are the algorithm. Okay. So take a screenshot before you lose it. Okay. Okay. This is the problem we have. So W look ahead is equals to WT minus Y update T minus 1. WT minus Y gamma update T minus 1. Okay, so this is what we have. Let's see the problem. At step current gradients at the look ahead position del W look ahead is equals to, so that is given. Okay, so that is, so eta is learning rate, right? So eta is learning rate 0.05 into look ahead value is 0.3. This is plus gamma update minus 1. So gamma is 0.8 and update t minus 1 is 0.2. So this is the current update. Okay, how much it is? 0.16, 0.15, 0.015. This becomes 571, 0.075. Okay, this is the one. Okay, so you've done it. In optimizing neural network with NAG and iteration T, you have current weight W T. So this is 1 minus gamma is 0.9 and update T minus 1, is it known? It is known, 0.25. So this becomes 9 5 45 4 9 2 18 22 2.25, 1 minus, so that is minus 1. So this is minus 1 and minus 1.25. Okay, gradient at look ahead position del, this is given. So what they are asking for, I think update T is what they are asking for, I think. So look ahead we have got. Okay, this is the one. Now gradient is also given. Okay, I think they're asking for the previous question only, update T. Okay, for that what we need, gamma times update T minus 1, 0.25. Gamma times 0.25. So gamma is 0.9 into 0.25. And then what we have is eta times, eta is 0.01 into delta look ahead minus 0.5. This is what they're asking for, I think. So this is minus 0.005. Okay, and 9 and this one 9, you've done this, right? This is 2.25, so 2.25, and we're subtracting this, so 5 1 is there, so 4 2 4, 2.245. I don't know what they're asking here, they have not written it clearly. Get the W look ahead, but what's important? I don't know what they're asking here, the question is not clear. I've not written it what they're asking for. We'll leave that question. Okay, anybody has any other doubt? Any other doubt? Okay, then we'll be stopping here. Okay, anything else you might want to ask? Okay, thank you very much.